Okay, thanks very much for the organizers for inviting me to this exciting meeting. Too bad we can't all be there in person, maybe next time. So I'm going to talk about history of gravitational lensing in cosmology. So I think the first, the sensible discussion of gravitational lensing in cosmology is this gentleman who probably worked on it when he was in confinement. And you know, in his books on optics, he starts with a set of 30 or so propositions that he calls queries. And the very first one is this one that I've highlighted here, which is, do not bodies act upon light at a distance and by their action bend its rays, and is not this action strongest at least distance? Another query he gives is the proposition that light is particles. Right? It's well known that he took the particle rather than the wave view. And combined with the knowledge 30 years old then that the light moves at the speed 3 × 10⁸ meters per second, he would have been able to calculate deflection of light, so on. Now, as a bit of an aside, you know, given that this history of lensing in cosmology, you might wonder why he didn't go further with this. So what I have in mind here is this statement by Milner McRae, who after the development of FRW models said, all of this could have been done by Newton, right? And the question is, you know, why didn't he do it? And what they have in mind is that, you know, Newton could have analyzed a uniformly expanding dust sphere. He would have obtained Friedmann's equations. And the key thing is that the radius of the sphere wouldn't have entered into any of the locally measured quantities, right? So you could take R to it to infinity. And the reason he didn't is revealed in some correspondence with Bentley, where he, it's in this quote below, where he's saying, yes, locally in an infinite universe, locally things will collapse. So it's amazingly prescient. He's doing gravitational instability, but he refuses to accept the idea that the overall background, as we call it now, would be dynamical. He's, what we'd say in astrophysics, that he's invoking Gene swindle, right? And he admitted to being, you know, not too happy about this, but it's a missed opportunity. Nonetheless, a little bit later in the 18th century, Mitchell and Laplace applied Newtonian theory, asking how big a star would be big enough would stop light escaping from it. That's not what we're talking about. But start of the 19th century, you've got Cavendish here and von Sollner, who applied Newtonian theory to calculate the bending of light by the sun. There's a bit of controversy here as to whether von Sollner actually got the relativistic factor 2. It has to do with the figure at the bottom right there, where there's some confusion as to, in the literature, as to what angle he was actually talking about. Is it? But I don't believe he got the relativistic factor 2, right? These guys predicted 0.84 arc seconds deflecting, and the calculations, you know, very simple. You just say, what would Newton have got for the deflection of a particle, a test particle moving at the speed of light past a mass with the mass of the sun? Now, as another aside, now we're in the 19th century, middle of the 19th century, you've got Maxwell, and, you know, Heaviside translated him for us to the form of the equations. And you might ask, well, why didn't Maxwell do gravity and this kind of thing? And Maxwell never really got started with gravity. And it's a shame because, you know, electromagnetism, it's a field theory, it's causal, it's relativistic, it involves gauge and so on. What tripped him up, he got the stress tensor for gravity. This is in the his Encyclopedia Britannica article. And it's the correct stress tensor. But then he worked it out and he realized that sitting in his room, there was a momentum flux of 32,000 tons per square inch. And he said, I do not think space is strong enough to withstand such a stress. Because you've got to remember, his mindset was, you know, that he didn't really get rid of action at a distance. He believed in lots of little actions. He believed in the underworld with cogs and gears or some kind of mechanism that transferred momentum. And so this kind of momentum flux, he just threw up his hands in horror. But, you know, if you look at least in weak field gravity, you know, it would have been a relatively minor advance for him to develop a relativistic weak field gravity, but it didn't happen. We had to wait until the start of the 20th century and Einstein, and then there's a rapid sequence of events. Around about 1910, he's thinking about principle of equivalence, and he predicts 0.84 arc seconds for the bending of light by the sun. And there's controversies around this. And there were two experiments to try and measure this, both of which failed, which is good because they would have proved him wrong if they'd have succeeded. And in 1915, he publishes GR paper, more controversy, but now it's got this factor too, that the light bending by sun is twice as big. And we all celebrated a couple of years ago, the centenary of Eddington's trip to measure this in Principe, and Einstein became world famous. So, you know, what actually happened in that brief period between 1910 and 1915 for him to get it right? So he starts off apparently stimulated by reading about a tiler falling off a building and thinking, well, yeah, as he's falling, he doesn't measure gravity. Gravity and acceleration are equivalent. And then, you know, he can modify the metric of special relativity to include a warping of time, right, as indicated there. And that allows you to explain a lot of phenomenology of gravitation, why things move on parabolic paths if you throw them, and it predicts the gravitational redshift. And from the gravitational redshift, he gets the light deflection. And the argument here is that as the light goes deeper in the potential, its frequency increases, so its wavelength shrinks, so you can figure out how much light is bent. You get Snell's law, right? You could also get this by thinking about an accelerated observer on the surface of the sun. What would they see for the deflection? Right? That's where he is in 1910. By 1915, I don't need to explain to you, this audience, that he's developed the field equations and so on, beautiful parallels with Newtonian gravity. And now if he does weak field gravity, he gets this, what we call the Newtonian limit or weak field metric, slowly moving sources, and so on, where now, as well as the warping of time, there's the second term is the warping of space that appears, and that changes the geodesic equation, now gives twice the deflection. Now, cosmologists use a sort of optical, an analogy that the universe is just like lumpy glass, right? That if you've got this weak field metric and you ask, well, how does light particles move, they're null particles, then this is their coordinate speed of light varies from place to place. And so you say that's like an inhomogeneous medium, or, you know, say radio waves in an inhomogeneous plasma or something like this. Maybe that's not a very good analogy, but anyway, you know, well known. Lots of we know how light behaves in glass and so on, and so from that you get Snell's law. I always get called up in or called out in France for not referring to Descartes, who they attribute Snell's law of refraction to Descartes, but I always reply that in fact it was Ibn Sal who did it in the year 984. Anyway, what you get is a law for how rays are deflected with the factor 2 in it, so twice what Newton would have obtained. There's a warning here, though, that, you know, this seems like a nice, simple analogy. We all like analogies, but at a very basic level, it's terrible, because in glass, the speed of light varies from place to place, but the frequency is fixed, right? If you're inside a swimming pool and you look at light from the outside, there's no red shift or blue shift. Whereas in gravity, it's the opposite. The frequency changes because of the gravitational redshift or blue shift, but everyone measures the same speed. So you have to be careful with this. So what are the observables that you can measure? The most fundamental one is the gravitational time delay. So here's Shapiro's formula. And you actually measure this along with the geometric delay in strong lensing with multiple images of quasars, and George mentioned this before. I want to mention the paper by Blanford and Narayan, which for, I think, a whole generation of us in lensing were stimulated by that particular paper. It's so beautiful. And if you haven't read it, I strongly recommend it, where everything starts from the time delay surface and you derive everything from that. The next thing you can get is the light deflection if you integrate Snell's law. And this is going to be very important in the last part of the talk, is the light obeys has a random walk, and so you've got to add in quadrature the effect of different deflectors along the path. And then this is sketched here. Well, then you can ask, well, given what we know about large-scale structure, what dominates the deflection? And it turns out to be supercluster scale structure, things as 30 megaparsec scale, give or take. And they produce deflection of about 10 to the minus 3 radians, so it's somewhat hard to observe. And then what is more directly observable is if you now take the derivative of the deflection, you get a 2 by 2 tensor, which describes things like the magnification of images and the distortion of their shapes. And this has got a very different dependence on scale. This is quite weak at large angular scales. At degree scales for sources at redshift 1, it's about 1%. But if you extrapolate down to smaller scales, it gets bigger and bigger. And it was George, again, who was really, you know, held our feet to the fire and said, you should take this seriously. For all you know, this blows up in your face. And we'll come back to that later. So here's a non-complete list of some of the applications of lensing in cosmology. I'm just going to talk about a few of the ones that I've highlighted, but in boldface there. So strong lenses, first one was found when I was a student, and it was very exciting. And 2 images, actually 3 images, separation between there's a close pair, and the third one 6 arcsecond. And from that, you can do things like measure the mass of the galaxy. And as was pointed out by Revstal previously, because the background quasars varying with time, you can measure the light travel time distance. And that's on the order of the deflection angle squared divided by h naught. So it's a path to the Hubble constant, though a somewhat uncertain one. What about the weak lensing was really started off by a fantastic paper that I'll mention at a few points going forward by Zeldovich in 63. And there's just a throwaway comment at the end where he has beautiful little sketches showing how galaxies will be distorted. Though for the most part, it was concentrating on how the flux densities of things will be affected. Rachel Webster thought about how the shapes of galaxies will get more and more distorted at higher redshift. That's not really weak lensing, which is simpler. It's a sort of linear probe. And it was in the mid-80s that really Tony Tyson and his group started presenting results on weak gravitational lensing. There was another weak lensing result, which was Quasar galaxy association. So this is an exciting time. Very little was known about the large scale structure of the mass around galaxies or on larger scales. And what was particularly exciting, that these two probes seem to give contradictory results. So I can no longer advance my slides. Roy, can you hear me?
Yes.
That's good. So we're still connected.
You're still connected. You can still see the slide, early days of weak lensing.
Okay. This is annoying. The screen is completely frozen.
Try restarting the share.
Yeah, unfortunately, I can't see my cursor. I don't know what I can do. This thing is completely frozen up. Any suggestions? Control keys.
I have a backup copy of your slides. Maybe I can try sharing that, and you can just tell me where to advance it. Maybe you can.
I'm going to try and rejoin the meeting.
Okay.
I see you're back with us, Nick. You are muted. Sudan, can you unmute Nick for him?
Okay, I'm unmuted. All right, let's try again. Something a bit nasty happened because
there we go.
Right. I think I'm not going to go to full screen because that was may have been causing the problems. So what are these early days? Quasar Galaxy Association, Claude Canizares and John Peacock wrote the first couple of papers on this that I knew about. What happens if you've got a quasar that you see through the halo of a galaxy? And naively, you think, well, the galaxy's going to lens it, amplify it, make it brighter, so I'll see more of those things. The reason was that there were, quasars were thought to be cosmological distances, but there were some cases where they seemed to be associated with foreground galaxies. And the people who pointed that out were considered cranks in the community, but they were right. What they were seeing was this gravitational lensing effect. The theory here is that, yeah, lenses will make things brighter, but it's a little subtle what you actually see, because the way sources get made brighter is by magnification, then that dilutes the number of density of sources on the sky. So you see fewer faint sources and more bright sources. And then that was the prediction. People measured it, and they measured what seemed to be about a factor 3 larger than we believed to be realistic. And then the cosmic shear, CCD devices had been invented, and so people were starting to do relatively wide field astronomy, and it was Tony Tyson's group that pioneered this, and they in '83 they produced a couple of papers. One of them is illustrated at the top, which is measuring what we'd call cosmic shear, measuring the mean polarization of sources in a set of, I think, 30 or 40 different fields. And they got a null result, not too surprising, but bear in mind there was a great deal of uncertainty in what the large-scale structure was. The other thing they did was galaxy-galaxy lensing, which is the lower plot, where they got a null result too. But here, the dashed lines, actually the lower dashed line shows the prediction, a pretty realistic prediction. And so here, the lensing seems to be giving a lower mass than we thought was there. This all got sorted out. But the next thing was moving on to clusters of galaxies. About 5 years later, '89, Tony produced this paper where he made very deep images of the cluster Abell 1689, subtracted off the red foreground galaxies from the image and looked at the ellipticities of the background galaxies, and did a very sort of ad hoc modeling, which came up with this image at the bottom. And so this was, I can't overestimate, how exciting this was and what a huge impact it had. What was clear was that this was a signal coming from the bulk of the background galaxies being distorted. And big deal, you might say, we knew that was going to happen. But you could then extrapolate and say, well, what would I see on larger scales? This was an existence proof that proved there was high signal to noise to be had on large scale. The questions were numerous, though. What was this colorful image actually measuring? Surface density, projected potential? Who knew, right? And this null result for galaxy-galaxy lensing, that was revealing a problem with calibration. All of this had to be figured out, and was done so in the next few years. So I worked on some various parts of this, understanding what was being measured, inversion techniques, how you would make a properly calibrated mass map, how you would apply this to measure the power spectrum of density fluctuations. And as you know, this has produced lots more things. Here's a state-of-the-art example by a postdoc at LPNS, produced just recently from the Dark Energy Survey. And the next decade is going to be a golden age for this, with things like LSST, Euclid. Tony deserves all the credit for just having hammered away that we need dedicated instruments to do this properly. And a little bit later, we will have the SKA. So now I'm going to do a little intermission and make this a bit more interactive and have a little quiz. I hope this will work. I set this up with Sudan earlier. So far, I see the quiz. That's good. So far, what I've told you is a bit disappointing for GR theorists. It takes you years to learn GR, and then for lensing, it seems you can get everything by using Newtonian theory and just adding a factor 2 for relativity. And I already pointed out some of the dangers of this, but let's just pose a little quiz here. So 1915, Einstein's prediction is twice Newtonian for the sun, and guess what? Eddington confirmed it. Well, what if you were to actually measure the bending of a horizontal light beam while sitting on the Earth? Right? What would you measure? So the options are twice the Newtonian prediction, something else, or something that's, when I've tried this before, some people say, I don't like this question. It's ill posed or something. So go ahead. Hey, this is cool. We don't have that many. Oh, 14 people. Good. This is anonymous, by the way. So don't worry. I'm not going to share the grades with anyone. We're up to 24. Last few seconds, anyone who's indecisive, make up your mind, because I'm going to close the poll in a few seconds. I think we're sort of converging. And this is very interesting. So we've got the highest ranked is the Newtonian prediction, and that's the right answer. That's the answer Einstein gave in 1910. But notice it's not trivial, right? You guys are experts on this. How do I get rid of the poll? It's not that many fewer thought the answer was the 1915 result. And interestingly, just want to get rid of that window. Sudan, can you get rid of it? So if we have time, we'll come back to that right at the end. Probably won't. Unfortunately, it's blocking my screen. We should have tested this.
Is it still there?
It's still there, unfortunately. Maybe I have to stop share and start share. I got rid of it. I'll start sharing again. Sorry about that. Interesting. So good. The majority, the highest ranked, but not an overall majority, got it right. There's another question I'd like you to think about, and this is this famous 63 Zeldovich paper, where I think he's the first to calculate or to draw these cone diagrams. So you think about an observer and a bundle of rays going back across the universe to a distant source, and ask how that bundle gets focused or defocused. At the bottom of these pictures he has at the end of how circular galaxies would get distorted. The left-hand plot at the bottom is cosmological distances and so on. But what everyone calls this paper is it's Zeldovich's empty beam calculation. He said, what if we looked at a source, but there wasn't any matter in the beam? And he convinces us that there would be no focusing because there's no matter in the beam. This raises an interesting sort of question. Here's a sort of an illustration of what he has in mind. And what I'll ask you later, if we have time, is this a case where this Newtonian ×2 works, right? If you were to imagine firing non-relativistic test particles up this evacuated tunnel, this is the empty beam in an otherwise homogeneous universe, would there be a gravitational field? Would it cause those test particles to diverge? And would light particles be the same, putting in V equals C and just cranking up it by a factor 2? So it's Geraint Lewis who posed this problem to me. This sort of strips it down to the minimum. But let's move on. Just think about that if you find the next few slides a bit boring. I want to talk about another historical story that started with that paper by Zeldovich. Right? So here's the Planck sky map, and from which we conclude that for any sensible H0, we live in a spatially flat universe. But in making that kind of cosmological parameter estimation, we're assuming that we're looking at a surface at a distance from us, which is given by the mean distance for the redshift at which we know the CMB was released. The other thing, pillar of cosmology, is the Hubble diagram for supernovae 1A, which again, in a similar way, assumes that there's no bias from lensing. So the question now is, well, is there a bias? I mean, so what we're talking about is things like angular diameter distances and the CMB, luminosity distances for supernovae. And I think most people would accept that these, with lensing, with structure and the associated lensing, these things become random functions of position on the sky. Things can be amplified or de-amplified. The question here is not that, it's whether there's a bias, right? Does the emergence of structure in the universe bias these distances, right? And Zeldovich, very quickly, Zeldovich was arguing, yes, if you look at things, see things along empty tubes, right? And the way he gets this, or one gets this, George introduced Ray Chowdhury's equation, comes very directly from the machinery, basic machinery of differential geometry, that you can measure what is in fact the enthalpy, this quantity here along the line of sight, skipping forward rather quickly. I don't have time to talk about some of the rather interesting issues cropping up here, but this seems to say, well, if there's no matter in the beam, then there won't be any focusing. And 64, Feynman gives a talk on this at Caltech, didn't write it up, but Jim Gunn, who was in the audience, did, and came to similar conclusions. Ron Kantowski, 69, Swiss cheese models. Charles Dyer developed this further, put in a cosmological constant, and everyone up to this point is singing the same song, that the emergent structure in the universe is going to make things look a bit fainter. And then there's an important paper by Weinberg where he pulls the rug out from under everyone's feet and claims that at least if the lenses are transparent, there won't be any effect. And his argument's very simple. He says, put a source at the origin of coordinates, think about observers on a shell who see that source with a given redshift. They've all got telescopes. Some of them see the source brighter, some of them see the source fainter, but conservation of photons, the photons have got across that surface. So on average, the flux density can't be biased. Okay, end of story, you might think. Weinberg's a smart guy. Not quite. Peter Schneider, working with Jürgen Ehlers and his student Stella Seitz, came up with a couple of theorems, one of which is very interesting, which is the focusing theorem using Ray Chowdhury's equation and showing that actually structure in the universe is going to make things look brighter. So what are they doing? We've got an equation here. Consider this a bundle of rays going back from your telescope across the universe. It's got some area A. Take the square root of that, call that D. D obeys this equation, right? R is the Ritchie focusing. It's the matter in the beam. So you might think of it as being the mean matter with some fluctuating part. And if that's all there was and the fluctuating part averages to 0, you wouldn't get any bias. You'd be able to use the homogeneous universe. But there's this extra term, right? This looks like, well, I won't say what it looks like. So this term is the rate at which the ellipticity of the beam is changing squared. So it's a positive thing. And that's what gives you the bias they're talking about. And if you estimate roughly what it is, it's big because it goes like the mean bias in the distance goes like the mean squared shear. And that is the thing that George taught us is potentially divergent at large scales. So following that, Kibble and Liu wrote an important article pointing out that Weinberg says flux densities are unbiased, but that's averaging over sources. They noticed that if you averaged over directions, and maybe with the CMB, that's what we talk about, you get something different. So Weinberg's saying the mean magnification mu is equal to 1. Kibble and Liu say that if you average over directions, you'll get something different. And what's going on, I've tried to illustrate here, is that imagine a situation with an observer surrounded by lensing stuff with some overdensities and underdensities. The fact that the underdensities cause the rays to diverge means that more of the sources will be seen through underdense regions. Right? There's a bias coming from that. And now that's all pretty old history, goes back to 63, we're up to 2005. The recent developments came from people responding to George's push to do nonlinear perturbation theory calculations and see if there are biases. This is hard, but it was nicely reviewed by our chair and his collaborators in this nice little letter. And they're claiming there's an effect. And in fact, this is perhaps the most interesting formula. This agrees with what you get from Schneider, Jürgen, Ehlers, and so on. So that's so the question now is there a flaw in Weinberg's argument? And George in '98 had come up with a sort of strong lensing argument for how this might break down. And he's already shown that picture. What Roy and his collaborators were doing was perturbation theory And what they proposed is that Weinberg's argument is wrong because he draws a sphere, that a surface of constant redshift isn't a sphere. It's maybe qualitatively like a golf ball. And that kind of wrinkling can surely make the surface larger. So this is where John Peacock and I came in and tried to calculate this. And we posed the question this way. We said, imagine there's structure in some region and we look at these sources or the CMB at great distance. How will, say, the surface of constant redshift for sources be affected by this? And how will the area of that surface change? And we argue there's two effects because the light follows wiggly lines, so they don't, in a certain amount of cosmic time, say, they don't get as far. And the other one is that the surface is wrinkly and so has a larger area. So they have opposite sign. And now I will appeal to your intuition to argue that this is like calculating how much the area of that swimming pool is increased because of the waves. And it's not difficult to show that it goes like the angle, the tilt angle squared. It's a dimensionless thing. It can't be anything else. And the tilt angle in cosmology is 10 to the minus 3. So the tilt angle squared is 10 to the minus 6. So there is a bias, but it's extremely small. I'll skip over the details. The other point, though, and this is related to Kibble and Liu, is you can get much bigger effects if you average the wrong quantity. You have to be careful. To get an unbiased result, you have to average the right thing. And I have run out of time, so I'm going to, why don't I pop up this other question? Let's have a bit of fun. We have about 1 minute, right? So here's the Zeldovich empty beam business, stripped down to its simplicity, right? So you got to ask yourself, is there a gravitational field there? So consider two things. I either fire P's along that tunnel and they may or may not diverge, or I can fire photons. So which, if either of the beams get defocused? This is a harder problem, so I can see your thinking. Only one. Come on. So if we were right, you know, if the cosmologists who like to think that lensing is just Newton times 2, right, then presumably either there'd be no field and neither would be deflected, or there is a field and both will be deflected. We got 18. So we've run out of time. Okay. So people are at least not choosing something else, but we've got basically equal amounts here. And so the right answer here is B, that there is a gravitational field in such a tube. And you can see that most easily because the Laplacian of the potential has to be 0 there because there's no matter. But there is surely a radial variation of the potential, and that means there's got to be a transverse variation of the potential, and that causes deviation for non-relativistic particles. But the Ray-Choudhury's equation says all you care about is the matter in the beam. So the photons don't get, so I guess the people who opted for B, who got the right answer, no Ray-Choudhury's equation, well, so congratulations to you. And I better stop there. Sorry for going over a little.